Hello, welcome back to LP3 experiments. So today we will see the fourth experiment of uh, PLP3 syllabus. So the fourth experiment is about implementing gradient descent algorithm. Now this algorithm is important for many application in machine learning and deep learning. Actually, gradient descent algorithm decides the rate of learning means the parameters you can modify using this algorithm for the next step and optimum parameters we can get for ML algorithms. So parameter tuning is very required for ML. That is possible through this gradient descents. So let us see what is a gradient descent. So actually gradient descent is an iterative algorithm that is used for to find a minimum function or minimum cost that you can consider. So minimize the functional value or minimize the cost that is possible through this gradient descent. So this is an optimization algorithm used for minimize the cost function of various machine learning algorithm. Even in neural network also the learn by means of a learning rate, the parameters are changed. So that learning rate you can decide by gradient descent. So basically it is updating the parameters of learning model. So actually you start with a random point and move towards the local minima or global minima of the function so that you will get the optimum parameters of machine learning. So graph pictorially you can show like this. So this is your initial starting point and this is the gradient. Gradient is nothing but the slope. So slope is shown here. So how much step you can take? One, two, three, four. That is decided by derivative of the function. That is called as derivative cost. So slowly you reach to a minimum point from where you cannot proceed. So how you will find a minimum is by means of either a number of iteration or you can say the step size. The next step is less than the threshold set. So if these two conditions are met, then you can stop you will safely understand that local minima has come and those parameters are optimum which you can use for machine learning. So in our case means in this syllabus function is given. So for that function we will see how the function was. So initialize with a random number 2 and then take the derivative of function. So derivative of function y is equal to x plus 3 square. So that comes out to be 2 into x plus 3. And we will decide a learning rate that is 0.1. So move in the direction of negative of gradient and the step size is determined by learning rate and we will assume that it is zero point 0.1 and iteratively you have to find the minimum one. So next value x1 is initial value minus learning rate into the derivative. So that comes out to be learning rate is 0.01. So it comes out to be new value is 1.9. Now what we have to do, we have to do repetitive actions until we reach to the minimum one. So considering it as x1 now, initial value as x1, x1 as a new value. The next value of x2 will come out to be 1.8. So you can see slowly it is coming from 1.9 to 1.8. And our we will try to converge it to -3, the local minimum. So slowly we will iterate through these steps, do the same function again and again over time. Either it should converge to local minima or it should come less than the step size, that we cannot further decrease the x value. So these two conditions we will try to come to stop the algorithm. So two conditions are set. Select a precision variable in algorithm which calculates the difference between two consecutive x value. If it is lesser than the precision required, then you can stop the algorithm. Or if it exists because of the maximum count, means you have to set the iteration count or a precision. Using that, we can stop the algorithm. Otherwise, it is a continuous iterative algorithm. So while previous step size is greater than precision and iterations are less than maximum iteration, so these are the two conditions. You will do this iteratively. That new cursor is a previous cursor into the rate of previous x. So the previous step size is absolute of these two difference. So how much changes x is the step size. Then iteration is iteration plus 1 and it will continue until you cross the maximum iteration. That is how it works. So it has used for parameter setting in machine learning algorithms or in deep learning to find a minimum cost or loss functions. Similarly, it is used also in control engineering, computer games, and mechanical engineering to find the minimum cost, minimum parameters, cost, or for that function it is used in control engineering, computer games, and mechanical engineering. So now let us see its implementation. We will open a Colab and we will set the initial value as 2. So initial value is initialized to this. Learning rate 0.01, that is decided by the S, and a precision is considered as point not 1. So maximum iteration also set. So these are the parameters you have to set initially, and we will start with iteration with 0. df is equal to lambda x2 into x plus 3, that is the function derivative. So while again the same algorithm we will set here and we'll print iterations versus the current value and when our local minima occurs. So I have executed these programs and here is how iteration will go. So for example, iteration 83, it has become minus 2.04. Like that iteration will continue and almost around say 200 steps. Now the precision is checked minus 2.99 minus 2.99 like that. Our set is point not 1 value. So if it happens to be less than this, our iteration will stop. So it is almost, so if you check here, now the iteration is 571, and the precision means current x value minus the previous one is less than the precision, and therefore the local minima occurred at 299995. Our maximum iteration were 10,000, but it has come within a 571 iterations. So this is how you can set it for parameter optimization to find the cost. So it is very important algorithm used in many ML to find the optimum value of this. So that's why the gradient descent is important for us. And so you learn it by heart how it works. And always remember that we are trying to find the local minima, local cost, or optimum parameters. Thank you. Do watch the video. So we'll stop here.